Iris received her BS, her undergrad and master's degree in computer engineering from UIUC, University of Illinois at Urbana-Champaign, and then went on to pick up her PhD in electrical and computer engineering from University of Colorado in Boulder. Now, she has been on the faculty of Brown University since 1996, now holds a dual appointment as Professor of Engineering and Professor of Computer Science. Her research interests have centered on energy efficient and reliable computing from the system level all the way down to the device level. Most recently, this includes the design of robotic systems. She served as the program chair and general chair of ICCAD, the International Conference of Computer Aided Design, in 2017 and 2018, and the general chair for International Conference on Architectural Support for Programming Languages and Operating Systems, also known as ASPLUS, in 2019. She is the 2019 recipient of the Marie Pistilli Women in Engineering Achievement Award and the Brown University School of Engineering Award for Excellence in Teaching in Engineering. There's a lot more about Iris that you could find out if you just went to her website, but we are delighted that she's joining us today. So Iris, I'm going to hand it over to you to walk us through roughly, let's take about 35 minutes. This is a 45-minute session, so we can, hopefully we can have some time for questions subsequently.
Okay.
So take it away. Thank you.
All right. Thank you, Mandy, very much for the introduction. Really appreciate it. Really happy to be here. As you were saying, my talk's about scalable machine learning architectures for real-time energy efficient computing. It's going to be focused specifically on robotics because, as you said in your introduction, this is kind of where some of my research is heading recently. But real-time energy efficient computing is required for a lot of applications. So I think what I'm going to do is broadly applicable. What I'm going to show is broadly applicable. So when I talk about machine learning for robotics, I'm talking about taskable robotics. So a robot's ability to carry out tasks depends on its ability to perceive its current state of the world around it.
I was sorry to interrupt, but did you want to come a little closer to your mic? It's kind of hard. We're losing you.
Okay. I'm going to plug in. I try not to use this, and I was talking before, so apparently this isn't going to work. So
just make it a tad easier. Yeah.
Okay. Can you hear me better now?
Yes. It's still a little soft,
okay.
But then it's okay. At least we won't have you fading in and out, which seemed to happen before.
All right. Yeah, sometimes it happens. It should be okay now.
Okay.
Okay. So taskable robotics, thinking about machine learning methods that we're using specifically for, perceiving, detecting objects, understanding their poses. This turns out to be a really difficult problem, especially when you're dealing with complex, cluttered environments. So we've seen machine learning being applied to many different applications, including robotics, and they've advanced tremendously with the help of deep learning, specifically neural networks. That's enabled us to have both high accuracy and real-time inference for a lot of these applications, but it comes at a cost. And what I mean by that, first off, the neural network works as a black box. We don't know how it's coming about its decision. We just have a decision. Also, in order to get the high accuracy, it requires very large training sets, especially to squeeze out those last few percents of accuracy. You need more and more training sets. And this has a burden in terms of computational, financial, environmental costs to do this extensive training. And you even have to deal with issues of who has these resources, who gets to use these resources. And on top of all of this, you're still left with a vulnerability to errors, whether that's through benign or malicious means. This is due to overfitting or when presented with unforeseen adversarial environmental conditions. Let me explain a little bit what I mean by that. So the question here is, what happens to the neural network accuracy when objects are manipulated, whether it's maliciously or not? And here are some examples from other people's work. Here's a panda. It's recognized by the neural network by a panda, but you add some noise to it, all of a sudden the panda gets identified as a gibbon. Other examples where a single pixel is altered in different images, and all of a sudden the image in there is mischaracterized. And then finally, some of you might also have seen this example with a stop sign. You add these stickers to it, which happens naturally. You see this all the time in the real world. People put stickers on stop signs. But again, this neural network that's meant to identify stop signs now identifies this as a 45-mile-an-hour speed limit sign. And this, of course, can have really disastrous consequences depending on how it's being used and applied. So even slight non-perceptible modifications or what seems innocuous modifications to an image can be detrimental to the neural network performance and can also have can also drastically alter the behavior of an autonomous system. So what does that mean for robotics? What about robotic manipulation? Maybe an adversary can't directly alter images, but an adversary can, say, alter the environment of where the robot captures images. And this can happen naturally from natural environments. They can be altered that end up deceiving the neural network. They can create occlusion. They can modify the appearance of an object surface or darken a room. All these things can confuse a neural network. And they pose a particular challenge for robotics. And so what we're dealing with is this issue that we're relying solely on a neural network for making decisions, and that can lead to unacceptable or dangerous behavior. And so what we've been focusing on in our research in the past few years is how we're using the neural network. How should it be used? What kind of adversarial environments may confuse a neural network? And in particular, this third bullet, how we can combine neural network output with other inference techniques to improve performance, in particular accuracy performance. And in the end, how much does the neural network accuracy matter if you're using other means to help in the whole flow process? So just a little bit of background. We're talking about robot manipulation. We use this sense, plan, act paradigm. So first you perceive the world. You reason over actions that are afforded by objects to achieve a specific goal, say moving an object, placing it on a table or placing it on a counter, and then carry out these actions in terms of physical motion. So for us, the bottleneck is the perception part, perceiving the world. So we have this three-stage pipeline: object recognition, pose estimation. And so you can understand the orientation of the object, so the robot will know how to actually manipulate it. And then there's the robot manipulation. So past approaches that depend on a neural network, you say, are RCNN plus ICP. So RCNN is this region-based neural network approach that produces a single bounding box, or best guess, for detecting an object. And then IPC is iterative closest point. It computes the 6-degree pose using a point cloud of the bounding box, and then kind of iterates on it until it converges, and from that gets the pose of the object. So what happens in these different scenarios? So if you use RCNN to detect a Coke can, in this example I'm showing, on the left, if you have good lighting, if you have, say, light clutter even, the neural network can do a fine job detecting objects. And in particular, I'm looking for this Coke can over here in the middle. So it's identified the Coke can, despite the fact that the Coke can is inside a cup, it found the Coke can. But here in the middle, we have a dark scene, limited lighting, still light clutter, and it can't identify the Coke can. And then when you have heavy occlusion, even good lighting, you still miss the Coke can here. The RCNN model still misses the Coke can. And then finally on the right, you can't see so well from this image. What happens is that there's some tape on the Coke can. So the words Coca-Cola are covered up, but even that's enough to confuse the neural network, and it can't identify that object. There's no bounding box around it. So all these things kind of conspire to confuse the neural network, and it misses this object. And once it misses the object, then it can't recover this from missing the object. There's no point in doing pose estimation on an object that you haven't identified. So you're out of luck here. And these are problems that we've identified here that we've been working on. Same kind of scenario, just different objects here. What happens when you have limited lighting or weird shadows or more occlusions in different ways? These all pose problems for doing accurate object estimation and pose object identification and pose estimation. So our approach is to notice that, okay, the neural network is good, but we don't really want to rely solely on the neural network to make final decisions in identifying the object. So we propose this two-stage approach, combining neural networks with sampling methods, probabilistic sampling methods. The idea is filter distribution of decisions from the neural network through probabilistic inference. So we get a bunch of proposals from the neural network, not just a single bounding box, but many proposals, and then we're using the sampling-based search to explore over this larger state space. So then the idea is to be less susceptible to errors due to these adversarial environments. So the idea is not to focus so many resources on the neural network inference, maybe even spend less time training, not trying to squeeze out more improved accuracy from the neural network itself, maybe even use simpler neural network architectures, but instead we'll use it to get some initial guesses. We're going to instead focus our time, our efforts on making real-time learning versus these sampling techniques fast, scalable, and efficient. Because it turns out the sampling techniques themselves can be expensive. And so in the end, what we're after is real-time, energy-efficient computing in order to get this accuracy. So let me go through quickly what we're doing in our approach. This is called GRIP, Generative Robust Inference and Perception. So we start off with a robot that has a capability of giving us RGB images, so visual images plus 3D depth image that's collected from the robot. And then we're using a neural network, we're passing it through a neural network, but what it's doing is producing this heat map of bounding boxes. Many bounding boxes are basically samples to consider for this next stage. And then also we're collecting these 3D feature extractions of the observed scene that we're going to extract these features from the observed depth image to consider contextual geometric information that will help us prune out potential discontinuities. So then finally we get to the second stage. What we're doing is this iterative likelihood weighting function. That's a likelihood function that's computing the weight of each sample or how well it compares to the observation. And during this evaluation, what we do is we take a sample, we render a 3D point cloud, generating an image of, say, what the 3D object would look like at a certain pose. And then we assign a score to the sample based on how well it aligns with the current observation. And then we do some, we get some likelihood score from this, and then from that we determine if we converged or not. We converge when by checking to see if the samples compare by comparing the average sample weight to some predefined threshold. If it's above that threshold, then we return the pose with the highest weight. Okay, so again, so assuming we reach that convergence, then we've determined not just the object, but its pose, and then we can pass that information on to a robot, say, so it can manipulate in whatever way it needs to do, say, pick it up, move it, whatever is desired. Okay, so we've run some experiments with this two-stage approach. Our two-stage approach improves pose estimation accuracy by, say, 30 to 40%. Compared to end-to-end neural network approaches. And in particular, when you're dealing with these kind of natural environments where you, again, may have a lot of occlusion, limited lighting and things like that. And that in particular is what we were worried about. That was kind of our motivation for exploring this in the first place. Now, the second stage is what we focused on in our work for a number of reasons. Just first, because you know, the neural network design, that's a fairly well studied problem. What we wanted to do was understand out of what was going on in the second stage. Again, it uses this geometric model of the object to perform this Monte Carlo generative sampling. And it's this iterative likelihood reweighting process. It's taking this distribution and generates hundreds of samples of the object, each with a pose assumption. And then it's going to do this rendering step. It renders the geometric model of the object at its pose. And you know, along with this, we also have the geometric features that we're using as well to improve our accuracy. Okay, so if a rendered point is within a certain distance threshold range of an observed point, then it's defined as an inlier. And then we do this inlier computation. It's a linear combination of the confidence store of the bounding box, the inlier ratios for the point cloud, and the edge features and planar features. And then we do this resampling step to generate a new set of samples that are based on the current sample's weight distribution. All right. So we iterate through this. This is a loop that we keep doing over and over again until we've converged, as I've said it before. It's computationally expensive. It's slow and energy efficient. Okay, so we seem to have taken a step backwards in that regard. Okay, we're getting the accuracy, but we're not getting the kind of real-time energy efficient benefits, and that was the point of this work as well. So how do we deal with that? We're going to focus on, okay, where's the bottleneck? Okay, what are we doing in this iterative process? It's a likelihood evaluation that involves rendering, feature extraction, and inlier computation over many samples over and over again. So what are the main bottlenecks? We have expensive floating point operations, a lot of off-chip memory accesses, and serialized execution of each phase, even on a GPU. So GPU can parallelize some of it, but essentially this rendering, feature extraction, and inlier computation is done in series on the GPU, okay? And that makes it particularly slow. So our goal then is to figure out how to accelerate this process and make it more energy efficient. We build customized hardware to do this. And so what we're doing is creating these customized processing cores for fine-grained pipelining, focusing on the most computationally expensive part. And then we replicate these processing cores in order to execute multiple samples in parallel. So here's a little closer view of what we're doing, what's going on. We talk about rendering the object. This again, it's computationally expensive. It's converting an object to some an image of what it would look like as a 3D image. And it does this one triangle at a time. Triangles from, converting the triangles from the geometric model to a raster image. And along with this, it's taking this edge information that's obtained in parallel with the rasterization. But the trick here is it's doing this in parallel, and it's doing this with minimal additional computational effort. It just turns out that it's a little bit of extra Boolean logic to do this. So we have these two operations happening in parallel here. We get the depth image and the edge image, and then we can compute the inlier score after this. But it's done all in this pipeline fashion, okay? And we kind of accumulate through this pipeline process the inlier score at the end, and then can operate on that, figure out if it's an inlier or not, do some resampling based on the scoring of the samples. Okay, so it's through this understanding that we could pipeline things in hardware in a way that we couldn't do with the GPU because of the restrictions on how the GPU is designed in hardware. There's another part of it, the sorting, sampling, and diffusion we also implemented in hardware. We did a few tricks there in terms of memory accesses, reducing those in terms of sorting things so we didn't have to go through all the weights. So there's a little bit of optimization there as well. But the main part was those raster cores that I just showed you in the previous slide. All right, so a little bit with the experiments that we did. We did this in hardware. We mapped it onto an FPGA. In our case, we used the CCU 102, runs at 200 megahertz. And we compared it to these two different GPU platforms, a Jetson, which is a low power, energy efficient GPU, and this high performance Titan XP. Notice that they're much better resourced than the FPGA if you look in just terms of computational resources, memory resources, but also the clock speed. It's a lot faster than the FPGA. In our design, we're processing 620 samples per iteration. We designed 10 raster cores to fit on our FPGA. So we have to reuse these cores until all 620 samples are processed. We implemented two different versions of the GPU design. One is just implemented solely on the GPU and does everything on the GPU. The other one splits it between GPU and CPU. The idea there is the CPU kind of naturally can process, do the sample initialization, resampling, and diffusion on a CPU because these are sequential operations. So it may seem natural to do that. That's how we wrote it the first time. And then we also implemented where everything was on the GPU design. So here are some results just for runtime, first off. Okay, so this is compared against the Titan, so our high-end GPU, compare that to our FPGA design. And you'll notice that, first, two things. So the blue is showing the implementation on the Titan where we use the GPU and CPU of the Titan. And it turns out to be significantly slower in large part because of this significant overhead for transferring data to and from memory. Something like about a third of the execution time was just devoted to this memory data transfer. So that was a good lesson to learn there. Be careful about that. But even with that, even when we implemented everything on the GPU, we found that the FPGA version wins even with its slower clock and fewer memory and compute resources. And if we look at the results I have on a table here, I'm also showing the Jetson results. The Titan takes about 40% longer than our FPGA design. The Jetson takes 20 times longer per iteration. And this turns out to be, if we kind of take all the execution time, we have to iterate until we converge. It takes about 50 iterations until we converge. It takes about 3 or 4 seconds to process an object. It actually is a little faster than that because as we get closer and closer to convergence, it actually takes less time to process because of more efficient memory accesses. So this was a really nice result that we got here. Again, what's going on here? Less time spent on data transfers, less need to store intermediate results, and more opportunity for parallel execution. All that was really important to improve runtime. And then also for the energy results, what we found that we did really well on that too. We're a lot more energy efficient than the Titan. Of course, that's a high-end GPU. But even on the low-end Jetson, we did a lot better. And so again, that was a nice result. Now, notice that we don't win if you just consider power dissipation on the Jetson, but you really win when you consider energy because we're so much faster than the Jetson. So conclusions, what we found. So generative inference is a powerful tool to use alongside neural networks. And with it, we achieved improved accuracy in scene perception. But we also found that, you know, there's a cost to this, expensive. If we take advantage of hardware and hardware acceleration, we can get back a lot of the cost of that and still retain the accuracy. So we're 30% faster than the high-end GPU, using only 2% of the energy. We're 95% faster than the Jetson, the low-power GPU, using only 4% of the energy. So some nice results there. For future work, what we want to do is consider other accuracy, runtime, and energy trade-offs that can improve that number even more, both energy and runtime. And also looking into hardware acceleration of other sampling techniques, such as belief propagation, which is something that we're currently considering now. And just a final couple of slides, future of scalable, efficient machine learning, where are we going? I think that this was an important finding, and I'd like to see other people kind of exploring this area. You know, how are we using neural networks? We're spending a lot of time and resources on improving them, and that's fantastic. We've come a long way. But even with that, efficient neural network architectures will not eliminate all of the shortcomings. And so I think we should be considering more hybrid approaches that can couple use of neural networks with other machine learning techniques. So I showed the sampling technique, Monte Carlo sampling, but I think there's a opening for a lot of different machine learning techniques that can be coupled with the use of the neural networks. And I think this will also not just improve accuracy, we showed, but allow us to potentially offload some of the complexity that's involved in the neural network architectures design and also their training, which also has a cost that's not always kind of computed and shown up front. And then also these hybrid approaches may be more naturally robust to errors and adversarial attacks, and also dynamically changing environments. And I think that's also very important. So focus on efficient, scalable hardware acceleration for on-device learning techniques to complement these neural networks. And I'll end with this. If you're interested in learning more, you can visit my webpage. If you Google me, you can find me, but here it is through the CS department at Brown, you can find me. And here are 4 papers that I have co-authored on the topics that I just presented today. So I think that was half an hour, Mandy. I hope I met the time requirements, but that leaves open time for questions, which I'm happy to take.
That's awesome, Iris. Thank you so much for that. Let's feel free, folks, to type in your questions on the chat window and I'll read it out to you, Iris. But let's just start off with just an overall question here with respect to scalable ML architectures that you're. Can you speak to some of the applications that you envision this targeting? Is it going to be a panacea for all possible applications, or is there?
So as I said before, the focus was on robotics, right? And what we were dealing with is robot manipulation. And what do you need to do that? It's about perceiving your environment. Okay, so if I focused on that part, right, you want to understand what's going on in your environment. You want to understand where are the objects? How are they oriented? And I guess if you just focus on that component, all right, that can have a broad range of applications.
Yeah.
All right, I'm trying to identify what's going on in my scene. It can be used for vehicle navigation. It can be used, object avoidance, or finding objects, or whatever it is. That, you're not trying to necessarily manipulate them, but you really want to understand what's going on in the environment. And there are many things that can confuse the machine learning, or the neural networks that are used in that. And that was kind of the motivation there.
Okay, so that's great. But so looks like the focus is on perception, but then when you start thinking beyond, as extending that, looking at perhaps reasoning, maybe some kind of decision making, based on what you perceive or what you interpret. And I suppose that would be your future steps moving forward.
Yeah, so that's a very interesting question. And I think that could also be generalized, right? How are we use this neural network, okay? It does a great job learning. We can train it to make all kinds of decisions for us, okay? But there is this risk, right? That we're letting it make decisions,
yes,
okay, based again on this black box, all right?
Right.
What if we stopped short of letting it make that final decision? What if we got just a range of proposals, a range of guesses from a neural network, and then we can kind of explore them in more detail, iterate on them in whatever means in more detail, okay? And by that, get more confidence in the decisions that we're making. And then we're also by doing so, getting some explainability. All right, then we'll know then how we're coming about this decision.
Yeah. Yeah, that's great. It looks like we have a question from someone here. Do the evaluation results include DNN as well, and is it end to end? Iris, question for you.
Okay. Yeah. So right, the results I showed you were just for the second stage, for the sampling, and I was showing you for a single iteration. So that was milliseconds, and that's why I'm saying multiply that by 50 approximately, because that's approximately how many iterations it takes before we converge. Why didn't we measure the neural network time? Because that was fast. That wasn't the bottleneck. Okay, that once you train your model, it's getting these bounding boxes very quickly.
Okay. All right, thanks. Again, folks, feel free to type in your questions on the chat window, or if it's easier and you want to unmute yourself and ask a question, go ahead and do so. Okay, while we're waiting for another question, Iris, I'm just wondering if you could actually comment on the security aspect of it. On one side, we talk about having energy efficient computing, but I think one of the challenges that we are facing more and more is the security of the whole setup. And is there a concern or maybe a challenge here that once you start looking at ensuring that you move away from energy efficiency, which I believe is one of the focus points of wanting to look at this, right? So can you share your thoughts on that?
Yeah. So right, by using this two-stage approach, we are moving away from energy efficiency, right? If you could do this with, say, the RCNN plus iterative closest point that I was talking about earlier, then it would be faster and more energy efficient, but you wouldn't be getting the accuracy that you need, right? And so from a robot's point of view, maybe you pick up the wrong object, or it can't find anything, or whatever it is, right? And so energy efficiency doesn't matter if you can't do the task required, right? And so one part of it is, so okay, let's get the energy efficiency back. We need hardware in order to do that. Okay, let's figure out how to do this in a custom way to get the energy efficiency and the timing back. But getting back to your point about secure security issues. I do, actually, when we first started exploring this, we weren't dealing with the energy efficiency part. We were dealing with the security part. We wanted to understand that how vulnerable, say, neural network-based approaches may be if somehow the environment was altered in some way. This could be benign, right? But it could also be malicious. What does it mean to, if you turn off the light in a room, are you doing that, to save energy, or, or maliciously because you're trying to confuse the system? And that could be a means of attack. If you alter the surface of something, maybe because, hey, I'm gonna replace the Coke can with a different type of cola, maybe that's okay. But what if you did it maliciously? Or what if in the end you picked up not a Coke can, but something else, an explosive device, or whatever? You could think of different scenarios where we need to be careful with how we're using our neural networks. They're trained in a certain way. We make certain assumptions when we train our neural networks, and that's just fine most of the time, but can be really, really dangerous some of the time. And if someone has some devious imagination, it could be really, really harmful.
Right. Right. All right. I see another question on the bridge here. What are the reasons to choose FPGA as a platform for implementation? Are there any expectations about a future circuit design here?
You mean like beyond FPGAs?
I suppose, yeah, that's what I would do.
Yeah. So certainly it would be nice to be able to do this in a custom design, an ASIC design. And I think that, certainly it would give you more efficiency, right? It would be faster, it'd be more energy efficient because you wouldn't have to deal with the constraints of an FPGA. And we could also squeeze out more, raster cores, for instance. We were using only 10 raster cores. If you had more raster cores, you could process more samples in a single iteration. And I think that would be great. What I would like to do is design these kind of in a more generalized way. So as you're saying, Mandy, I showed this for pick and place robot manipulation, but you can imagine you can use this for other applications. So I would like, and this is what I'm looking into in the future, is kind of generalize this. Can I build some kind of library? So, here you are. This is how you can implement monocolor sampling very efficiently in hardware. Here's kind of an ASIC design for doing this, and then implement it or integrate this into your whatever application you want.
Mm-hmm. Yeah. Okay. All right. There's a question. This is from Jason. Iris, you showed some examples about how a DNN can be tricked. Example, a stop sign. On the other hand, we humans are much harder to trick. Is it well understood why that is so? And can ideas be borrowed from that DNN human difference to steer DNN training to make it more robust or harder to trick?
Yeah, that is a great question. So I want to say yes. Okay, still TBD, right? How can we do this? And I'll say this from my own work. Okay, here's something else that I'm trying to understand is, can we capture something about how humans think and integrate that into a neural network? And I think, Jason, that's what you're asking. And so one thing that humans are really good at is understanding causality, right? That if I do something, I'll get this certain behavior because I understand the underlying cause of why this is so, right? But machine learning has no sense of causality, right? People are trying to extract causality from machine learning or from neural networks, but it's not, it doesn't, the neural network doesn't really know causality, but humans do. And if we can figure out a way of modeling that, capturing that information and inserting it into a neural network model, I think that would be fantastic. I think that would be a huge game changer, and would allow us to solve kind of more complex problems and also make us less vulnerable to these types of errors. So I'm actually just starting to dabble in that. Of course, you know, causality may be just one solution to tackle this problem, but part of this bigger picture of, you know, how are humans really thinking? And we're getting it right part of the way with this neural network, but I think that there's still some elements that we're not quite capturing, and we're trying to get around it in maybe a forced way or maybe a brute forced way, to try to get the neural network to operate like a human brain. We're, you know, we're not quite there yet. I think we're a ways to go, actually.
Yeah, we're all trying to figure that one out.
Yeah.
And at the power levels that the brain operates on, right? What is it, 20 watts?
Yeah. Yeah.
Right. Okay. Are there other questions? Again, feel free to type in your questions, or if you want to unmute and ask, feel free to do so. Let's see. I don't see anyone else. I'm looking at the time here. We're close to the end. All right. If it looks like there aren't any more questions. So Iris, did you want to, you know, as part of this, a lot of the attendees are students, and they're very excited. And this seems like the, you know, really like the cool area where everybody wants to partake in or be a part of. So do you have any, you know, closing message for them as they, you know, can try to seek out
parting words of wisdom, or
parting words of wisdom? Yes, yes, why not?
Don't be afraid to take on the hard problems. It may take longer to get to a solution, but I think asking the big questions, I think, is a really important step to exploring the, you know, really worthwhile, rewarding problems. Yeah. You know, and maybe, you know, things like I said, well, you know, what is going on here? You know, Jason, you asked a great question again, I think, right? You know, what's going on here? Why is it that we can trick these neural networks in a way that humans would never be tricked? How can we rethink differently, and let's remove ourselves from how we've been doing things in the past and try to reimagine. And I think that there's a, you know, bigger reward down the line if we do that. I'd like to do more of it myself.
All right. All right. Thanks, Iris. Thank you very much.
Very welcome. Thank you again so much for inviting me. Really appreciate it.
Yes, thank you for joining, and thanks everyone else for attending. That wraps it up for day one. And we will be back tomorrow, 8 a.m. Pacific, to get started with we'll kick it off with our panel. Right.
Great.
Thanks.
Thanks. Bye-bye.
Again. Bye.
Thank you.
Thanks.
Thank you.
Bye.